Hello everybody! Today we will discover how time is susceptible to manipulation. But first, let's clarify not a simple question: what time is? Obviously, this is what you see on your watch: date, hours, minutes, seconds. It's called a timestamp. A timestamp is present in most data packets coming from a GNSS module, but it's not enough for precision applications. There is a physical signal called PPS or pulse per second. The front of this signal is precisely aligned with coordinated universal time. I will show you. Well, we have a little update here. To see the PPS signals, we need an oscilloscope. I like Picoscope. Channel A is connected to the PPS output of the target receiver, and channel B is connected to the reference receiver. And please keep in mind a really important point: the reference receiver should not be spoofed in the experiments, because we need to compare the signal phases to estimate the success of the spoofing. And obviously, if the two receivers are spoofed, the phase difference will be zero. So the reference receiver should only receive true signal. To achieve this, you should use proper RF accessories with suitable directivity characteristics. In my case, these RF components provide at least 50 decibels of fake signal attenuation, 20 here and 30 here. This is the application for the Picoscope, and it's already configured for our testing. The red line is the reference PPS and blue is the target. And I set the trigger to the reference signal, this little dot here. And now we see the front of two PPS. The difference between the signals now varies around 20 nanoseconds. Unfortunately, I couldn't find how to enable automatic measurements of the delay between channels, so we will rely only on our eyes. Here we can see the time per division. It means how much time is in one cell here. Let's scale up to see the whole impulse. Let's try to set 100 milliseconds. Okay, perfect. Let's now run uCenter. To see the timestamp coming from the target receiver, let's go to Messages, UBX, Navigation, Time UTC, and here we can see date and time. Now let's run the simulator. And an important note about the time indicators in the app. Here, here and here in the log, all the time is in UTC format. Okay, let me align the windows a bit. Okay, perfect. Here we can see the reference timestamp and the timestamp from the target receiver. And here we can estimate the phase difference between PPS. Well, we start with a simple non-coherent scenario. Let's simulate past time. Time simulation mode, past time. And let's leave the simulation start time at the beginning of 21. When I click this button, the app automatically downloads files for the selected time range. Okay. And we are going to simulate the current coordinates, so the offset is 0. And I don't really want to show again the tricks with the JAMA to block GLONASS. You can watch our second episode to learn how to spoof a multi-constellation receiver. The link will be somewhere here. So I am going to disable GLONASS. UBX config GNSS. Okay, and apply. Well, I guess minus 50 dBm will be enough to block the reception of genuine signals. We will see. So I think we are ready, and let's get started. Well, here we see the clear picture of a non-coherent attack. Satellites are blinking here, the receiver has lost signal tracking, and the PPS has disappeared. Now we see that the false signals are clearly visible, but it takes time for the receiver to collect ephemeris information. Let's wait a little while. Yes, take a look over here. The timestamp has changed, and finally the receiver is spoofed. The PPS is in the wrong position, and that's the way it should be, because the spoofer signal is not synchronized with the genuine. Okay, let's now see what happens when I shoot down the spoofer. Okay, it's disabled. Let's wait until the receiver recovers and starts receiving live signals. Finally the timestamp has changed to the current time. And I think the receiver took about 30 seconds to recover. As you could see, even so obvious attack scenarios work. Let's try more elegant attacks. Okay, switch to the current time simulation mode. And let's leave the asynchronous mode. Update the files. Running. Well, here we observe the same behavior of the receiver as in the last test. Okay, it's spoofed. Here we see the correct date, but the time is slightly different from the reference. And the PPS signal is in the wrong position. Let's shoot down the spoofer and repeat the experiment. Okay, well, it's recovered. Timestamp is correct. Let's go again. Okay, exactly the same picture. The timestamp of the target and reference receiver are different. And the PPS phase is incorrect. Let's shoot down. In asynchronous mode, the simulator gets enabled immediately after you click the Start button. The simulation cannot start from the middle of a GPS data frame, only from the beginning. The duration of a GPS data frame is 30 seconds. Therefore, during a non-coherent attack, we always see a time difference between the reference and target receiver within 30 seconds. Okay, but if we want to control this process and get a predefined time of set, for example 10 seconds, let's see how to do it. Let's go to the time menu and let's switch to the synchronous mode. And there is the delayed start option. Let's put 10 seconds here and let's go. The application is now waiting for the beginning of a new GPS frame, but with an additional 10 seconds delay. We need to wait. Okay, it started up, and to look over here. The behavior of the receiver is quite different. It found and accepted the fake signals very quickly. Well, here we see a delay of 10 seconds between timestamps. Take a look at the PPS. It's in the right position. Let's zoom in. Perfect. The phase difference between the reference and target PPS is less than 50 nanoseconds. This is a very high accuracy. Let's see now how GLONASS can help here. Okay, as you can see here, I have already activated GLONASS, and I have decreased the output power level a little bit. Let's go. Well, the generation started. Take a look over here. GPS satellites are blinking, but the receiver does not lose the fix. Obviously, the receiver is trying to resist spoofing. Let's wait a little while. Oh my god, great picture, guys. GLONASS satellites have been excluded from the navigation solution, and even the JAMA wasn't needed here. I wonder if we can move the position. Let's check it. Let's open position deviation map. Let's go 500 meters west. Oh my god, it works. It's moving. Wonderful. Now we have seen one more attack scenario on a multi-constellation receiver. We didn't need a lot of power to suppress the real signals. This is a terrific, sophisticated scenario. I am sure that we will find a lot of such vulnerabilities. Let's move on to more precise attacks. Okay, let's do not change the timestamp. Just move the PPS by 100 milliseconds. Let's go. Okay. Take a look over here. Yes, great. The receiver instantly switched to fake signals. And let's wait. Yes, and finally the PPS has shifted by 100 milliseconds, exactly as we predefined earlier. Let's now try, for example, 200 milliseconds. We have to wait for the receiver to lock to real signals. Okay. As you can see, the PPS phase is now in place and we can start spoofing again. Let's go. Okay, it started. And exactly the same picture. Okay, great. And the PPS has shifted again. In the previous experiments, you have seen how to simulate the wrong time initially when starting an attack. Next, I will show you how to manipulate time in real time. Let's clear the start delay and reduce the power level to -80. And let's go. The generation has started. Here we can see that the receiver instantly switched to our fake signals. Why does this happen? The point is that during a coherent attack we generate a signal completely identical to the genuine one. And take a look over here. The PPS is in the right position. Let's zoom in to see the phase difference. Great, it's perfect aligned. Here we have three options for time manipulation. Let's start with the first one, PPS phase shift. Let's move it to the left by a few microseconds. As you can see, the step of the shift is always 500 nanoseconds. This is defined by the sampling rate here. If we increase it, the step size will decrease. Here you can see that the phase of the target receiver jumped by 200 nanoseconds. The internal clock is not adjusted instantly. It usually takes several minutes. And please note, when I apply a shift, the signal-to-noise ratio of the GPS signals decreases, and then it's smoothly restored. Let's check. Okay, did you see that? Once again. If moving the phase too fast, the receiver may lose signal tracking. Let's wait until the receiver adjusts its clock according to our manipulation. Okay, finally it's shifted, and I think it's clear. Let's stop the simulation and wait for the receiver to recover. So a few minutes have passed, but the receiver is still providing the wrong phase. I have to apply a cold start. Okay, it's all good now. So, in this experiment, we saw a typical scenario of a coherent attack. In the first phase, we generated a signal completely identical to the real one, with low power, and then we gradually shifted the PPS phase up to 2 microseconds. When we disable the simulation, the receiver switched to the real signals, but it still produced the wrong phase until we applied a cold start. Let's perform the same test, but shift the phase by 10 microseconds. Okay, let's go. Okay, great. And let's move the phase. 1. In the last two tests, we saw that the phase sometimes jumped by the hundreds of nanoseconds, because we moved it in steps of 500 nanoseconds, and we did that quite quickly. But is it possible to shift the clock very smoothly? Let's see. Let's go. The coherence scenario works perfectly, as usual. So let's apply the satellite clock correction offset, for example at 1000 nanosecond. Here we can see the offset value in real time, and it's going to be a long and boring process. Let's wait. So the PPS phase of the target receiver has taken its position almost perfectly. Well, we did a lot of tests with different attack scenarios. We demonstrated that the time of a GNSS receiver can be moved by years, by a few seconds, by hundreds of milliseconds. You saw precision attacks with a smooth, controlled time shifting, where it's not even necessary to block other constellations and generate high power. GNSS receivers carry plenty of vulnerabilities, and it's better to find them in advance to avoid significant consequences for your critical infrastructure. Don't forget to subscribe to our channel. Next time we will test the time saver.